welcome to the July edition of Seajure. People often ask like what we do here at Amperity because it's a little bit mysterious. We talk a lot about marketing, we talk a lot about telemetry. Really the core of what we're doing is entity matching, finding two records from disparate parts of the internet or even a customer's own databases and trying to figure out if they are the same thing. This problem is so universal that it almost found us as the founders Derek and Kabir and then Stephen were figuring out what to do to make marketers' lives better. But as far as Clojure, that's distinctly a choice. So for those of you who are into Clojure, I think it's safe to say that it wasn't the first language you learned. It probably wasn't what you were taught in school. It was a choice that you made because the properties of Clojure were beautiful, useful, and inspiring. So when these two worlds collide, we're here tonight to hear about how we've productively used Clojure to approach the entity matching problem. Yan, our chief data scientist, will discuss what Vamperity, an interesting way to think about kind of the core problems we're solving, and Chuck Sakoda will be speaking about actually how we used Clojure to solve these problems, the good, the bad, beautiful, and the ugly. So thank you guys. Take it away.
No, we're not talking about Amperity, we're talking Vamperity.
Oh, Vamperity.
Now
yes.
I have to change all my pronouns.
It will be entirely unclear what Vamperity refers to. Yan will tell you.
Totally unclear. So, welcome everyone. My name is Yan. I'm a data scientist. I'm excited to share a not very Clojure Vamperity story, but my colleague Chuck is going to talk about the challenges in building Vamperity. So, what is Vamperity? So Vamperity is a software startup excuse me, in Pacific Northwest. It's only 130 miles east of the famous Twilight town, Forks, Washington. Vamperity builds a product called Intelligent Customer Data Platform, powered by machine learning and some novel entity matching algorithms developed in-house. The core technique, entity matching, or can be called stitching, is like stitching. It's like a professional tailor trying to create a beautiful, consistent garment by merging different random pieces of cloths together. So through the entity matching pipeline, they are able to connect different databases together and create a single unified customer database. And with that, the marketers will be able to know their customer better than ever and reach out to them more effectively. So who are Vamperity's target customers? They're beloved consumer brands. For example, TruBlood, I believe you guys all heard of. So they are a leading synthetic blood manufacturer. So with synthetic blood, vampires do not need to drink real human blood anymore, and they can finally come out of the coffin and walk down the street like normal human beings. It's a great innovation. So now let's talk about entity matching. By definition, the problem is very easy to describe. So you have a large collection of records, and you want to group them into clusters where in each cluster the records are representing the same real-world entity. So it's like duplication process. But ironically, entity matching has a lot of duplicate names. For instance, record linkage, entity resolution, and my favorite one is this hardening soft databases. So it sounds like a simple problem. You probably wonder why you can't just group or join by unique identifier. Yes, you can do that only if your unique identifier is available in all the records across all the databases and truly unique, consistent, accurate, and stable across all the time. So in reality, it never happens. So you can use them, but you can't rely on them. Another big challenge is, unlike other machine learning problem, the entity matching problem, you rarely get the ground truth or training data. Take the TruBlood example, their customer database. To really get the ground truth, you have to call each customer or email them, ask them, are you guys the same person? But some of them don't even have contact information. So what does it mean is the ground truth is unknown and unknowable. Another big challenge is the computational complexity. So entity matching inherently is a quadratic operation. Basically, in the data domain, every record needs to compare to all other records. Without any optimization, you have to do that. But we're going to talk about how to simplify the process. So now let me walk you through the entity matching pipeline by showing you a TruBlood case study. So TruBlood recently just launched a frequent blood loyalty membership program, and they have some other existing databases, for example, the store visitor database and e-commerce purchaser database. So the TruBlood CMO really want to unify those three databases together to create a single view of their customer. For example, if some people are purchasing synthetic blood online, they will be able to know their skin color, and they can recommend some anti-sparkle sunscreen for them. So good use of the data. So this is the key steps of entity matching. First, you have a collection of tables. Then you do the data pre-processing to kind of standardize and normalize the table. And then you do the table union to concatenate all the table into one. And then you pass the table into the blocking stage. So in the blocking, before blocking, if you don't use blocking, every record has to compare to all other records. It's like the Cartesian product of the whole data domain. By using blocking, you reduce the number of comparisons to like almost linear to the number of the blocks you generated, but we will talk later. Then after blocking, you have a candidate record pairs, and you pass that to a classification phase. So at the end of that, you will know which pairs are representing the same entity. Then you pass those matched record pairs to union find. Using union find algorithm, then you build some connect components, and then you pass that to clustering, see if you need to further partition the connect component to smaller clusters. And then is stable ID assignment, which is Vamperity's novel algorithm to provide like traceable ID throughout all the clustering runs, so that the customer know how to track their customers. They have a stable ID. So the first is the pre-processing. It's very important to apply the entity matching technique on the clean and normalize the data. So we do some like simple process, for example, split the surname to surname the suffix, and also standardize and clean the email and address. And then we union the table by concatenate all the three tables into one by aligning the semantics fields together. For some tables, like the loyalty membership table, you don't have the skin color information, so we just fill that with a null. And the blocking essentially is, instead of comparing all the records in the whole database with all other records, blocking essentially is grouping the data into small blocks by their shared properties. For example, like shared phone number, shared postal. You can also construct some keys. For example, part of the given name, part of the surname, and part of the birth, the birthday. So only the records inside the block are comparing to each other. So what does it mean is we reduced the number of comparison from n square, n being the number of records, to k times b square. And k is the number of blocks, and b is the size of the blocks. So if you set an upper bound for the size of the block, then it becomes linear to the number of the blocks. So it's a huge simplification. Actually, this is an active research area People are studying how to reduce the number of records, comparisons, without sacrificing the recall rate. And after that, the related pairs are passed to the feature calculation stage. You can build some feature vectors like other machine learning process. For example, like the added distance of your name and the added distance of your email and gcard distance of your address together can be one feature vector. And you pass that to the classifier, and the output will be, is this pair a match or not? And then you collect all the match status and build the connect component. Connect component, by definition, is like every connect component is a connected subgraph, and there is no other positive edge between different connect component. So you're not missing any matches. But the connect component can grow very big. Even the neighbor record are very close to each other. The records on two ends can be very different. So Vamperity developed a few clustering algorithms by using different, cost functions, I guess. So correlation clusterings, for example, you want to maximize the agreement inside a cluster and minimize the agreement outside of the cluster. And Vamperity also developed a novel hierarchical clustering algorithm, basically split the cluster at where the conflicts happen. So that's basically the pipeline. And we run like the clustering algorithm every day, and we talk about like the customer really just want to have one ID for one customer. But the clustering structure changes every day. How can you establish that ID? So before we talk about how to do that, often I think solving a clustering problem is like solving a jigsaw puzzle. So how would you solve a jigsaw puzzle? So you have a pile of pieces, and you dig into the pieces, you find some interesting ones that's visible to you and you think can be grouped together by some shared attributes, for example, the patterns, the colors, and you kind of group them into little clusters, and then you dig into the pile again. You have a few more pieces, and you try to incorporate those pieces in those intermediate result of your puzzling game. And by merging those pieces, new pieces, to the existing clusters, the cluster can split, they can merge, they can split and merge, and you keep doing that. Eventually, you have a more complete picture, and the clusters will be stabilized over time. So, but unlike the jigsaw puzzle, the clustering process does not have the physical border, and you do not have a reference photo like the RAID. And so the clusters will continue to evolve, and subtly or drastically. So here we're going to show some actual dynamics of the process. So the first, you dig into the pile, you find some hair-looking pieces and some fabric-looking pieces. So you have this hair cluster and red dress cluster. Then you dig into the pile again. Then you have some face. And because the face coming, you actually, the red dress cluster has to break. And you took some pieces, and then you construct this like dude cluster. Then you found more pieces. It looks like a shoulder. So the hair cluster and the red dress cluster has to merge into one cluster. And then you found more pieces. Looks like those three can be grouped together and establish a whole new cluster. Looks like a wolf. And you continue to dig into that pile, and you keep growing the existing clusters. And you have like a grow cluster, a wolf cluster, and a dude cluster. So you probably wonder why I'm talking about this. It's like, I see where you're going, but why that matters, right? So, because the question we keep getting from, they keep getting from the customer is, like, for example, TruBlood. How many new vampires just joined the game? Like, how many new clusters? By new, I mean how many new entities you get in today's clustering run by merging new data, and how many vampires just left the program, and how to assign the remaining vampires with existing IDs so they can track them over time. So if you look at those two pictures, it's not really clear, even by using naked eyes, and it's not a big data set. So this girl cluster looks like she can get ID from the hair one or the dress one, but you really have no idea, like, this dude should get what cluster ID. And also they're interested to know have some metric to evaluate the churns between each consecutive cluster run. So if the data is bad, it's useful to have a healthy alerting system. So this is Vamperity's stable ID algorithm. You have two consecutive runs, step A and step B, and then you have, so in clustering run A, you have two clusters, A1 and A2, and A1 and A2 are the two cluster IDs. And in cluster B, you can temporarily assign the cluster ID to them. So you have a B1, B2, and B3. Then you can establish a matrix called confusion matrix to understand the relationship between all the possible cluster pairs between the clustering run A and the run B. So if you look at this matrix, the cluster the cluster A2 and B2 are identical. So intuitively, you would assign B2 the same ID, B2 the same ID, A2, right? And however, B1 share 3 pieces with A1, and B3 share 3 pieces with A1. So which cluster ID should A1 get the cluster ID of A1? Should B1 get a cluster ID A1 or B3 get a cluster ID A1? So intuitively, of course, B1 should get that because B1 has more overlapping items. So this is easy to solve, but think about instead of having 2 clusters, 3 clusters, you have hundreds of millions of clusters. So this problem can be formulated as a maximum weight matching problem, and a few techniques can be used, like Hungarian algorithm can provide a global optimal matching results, but it runs the cubic time. And the greedy algorithm can provide close to optimal results, especially when your cluster is not too connected, and it only runs linear time. So in the end of the algorithm, what we have is, okay, so we have A1 in the clustering run B, we have A1, A2, and B3. And in clustering run A, we have A1 and A2. What does it mean is, oh, B3 is the new one. So we have one new customer. They have one new customer. And 0 old customer have left. And there are 2 remaining customers, both inherit the ID from the previous run. So, and then the fourth question is about how to establish a metric to measure the churns between the 2 clustering runs. So there are a few available metrics, like the ranking arrow, the cluster arrow. Like we use this because it fit nicely with this approach. And the clustering arrow basically just count the number of non-diagonal terms of that confusion matrix after you do the matrix permutation and reach the optimal matching. So then we can apply this technique on each clustering step. It's interesting to see, like at a cluster, at a step D and step E, the cluster error is 0. It is because there's no churn. By churn, I mean merge, split, merge. So in cluster D, you only have a completely new cluster, nothing related to the previous one. And for clustering step E, you are literally just expanding the existing one. There is no conflicts in terms of ID sharing. So this is exactly what we want to measure. And then you probably wonder, like, hey, every day you have a new incremental data load in. Do you have to run the whole algorithm all over again every day? Because it can be expensive when you're dealing with hundreds of records. So answer is no. We have a good algorithm to do the incremental clustering. So before I talk about that, let's talk about Vamperity's summer party. Do we have one? Yeah, okay. So Vamperity is is organizing a summer party. It's deep in the mountains. It's so far from where the Vampirians live. So to simplify the logistics, the organizer has to figure out a smart carpooling algorithms to group the Vampirians who live close together so that they can share a car and get there on time. And there are tons of employees, so it took a while to run the algorithm. It's like a batch clustering algorithm. However, the vampires are very temperamental. They emphasize on RSVP. Some people still like accept the invite last minute. Some people like declined the invite, even they accept before. Someone complained, oh, this is not my address. My address already changed. So reflected in the database is like the insert, change, and delete. So the question is to deal with their temperamental character. Like we need an incremental carpooling algorithm. And what's the characters of those algorithms? Like desirable characters. Like first, it should focus on the updates. It should run much faster than batch, and it should preserve the same correctness as the batch. So this is the initial carpooling arrangement. So each hexagonal thing is like their home or like tombstone, whatever. So it's nicely arranged. You have 4 cars, but some people, some vampires, I'm gonna call them out. So like number 13, 14, 15, 16, they're like, you know what, I guess we're coming. And number 12 is like, sorry, I can't make it. And number 9 is like, this is not my address. Why you use the wrong address? So these are like the insert, delete, and change. So they have to run that over again. They run the batch algorithm again, and this is the final result they get. So the question is, can you run the incremental algorithm to get a similar results? So yes, the first step will be still blocking after you clean the data. So blocking basically just group the records into blocks that they share, like records that share the same properties together. But for this incremental algorithm, instead of creating like really the pairs inside each block, we only focus on the pairs that is related to the updates. So for example, if you look at a number, so this one, they use zip code for blocking. If you look at the zip code, if you look at the number 10 and number 8, they are in the same zip code, but they don't take the pair as a candidate pair. But number 8 and 15, 10 and 15, and 15 and 11 will be passed to the next step. And the next step is just classification or pairwise comparison. You want to find the positive edges. So what does it mean is if you're close enough, you're a positive edge. So for this case, Euclidean distance or just, the estimate time of travel can be used, and you can set a threshold, like only if you from point A to point B, you can take like less than 10 minutes, we can consider you a positive edge. So you have this. And the next step is quite unique. So for every positive edge you discovered, if it's related to any existing and not changed addresses, you need to find which car that was assigned to and pull out all the old carpool friends. So now we have all these carpool friends. And then they run the connect, the unify, find the connect component, and you have this. What's next? So, and clustering. It's really hard to fit 10 vampires in one car. So some clustering algorithm can be applied to break them apart. And some vampires are like absolutely don't get along. They can't stay in the same space. it's like hard conflicts. You can also use some clustering algorithm to split them apart. And then you can have your final clusters. But before we complete this task, there is one final step. And guess what is that? Alex, you were in the summer party. What is it? Okay, the very last step is to decide which card to take. So that's where the stable ID comes to play. I guess you guys all figure out, right? Yeah. Okay, that's the end of my talk, and I'm going to hand over to Chuck. Chuck's going to share some wisdom about building scaled system using Clojure and Spark. Chuck doesn't want me to use the word wisdom, but I think it's solid wisdom.
Thank you so much, Yan Yan. That was really fantastic. And a little about Yan Yan, since she's very humble. I work with her on her team as one of the engineers that brings Vamperity into the actual production environment. We've been working together for almost 2 years now, and I gotta say, it's just been a complete privilege to work with someone that's so knowledgeable and talented and hardworking as you are. So thank you, Yan Yan, again, and for your Yan-splaining just now, and for everything else. Okay, so you're taking this all in. You're remembering piecemeal that you're at Seajure, and you're wondering what all this has to do with Clojure. So that's what I'm going to try and share with you. How do we attack a massive, cool, challenging, kind of dynamic problem like Vamperity using a tool set that Clojure provides? And I'll say it's been no easy road. There's been a lot of struggle and a lot of strife on pretty much every part of our stack as we've done this, all the way from the Clojure code all the way down to our choices about RAM and NIC bandwidth and all kinds of little nitty-gritty details that as high-level programmers we hope to never have to deal with. But it's been an incredibly rewarding one, and I'll share with you a tiny little snapshot of what at least my journey's been like. And I'll try and point out the places, we're kind of take a little bit of a random walk here, but I'll try and point out the places where we're matching up implementation detail, technology choices, and so on with the broader problem that Yan Yan shared with us that, in that scope provides a lot of value to the potential customers. So you have to think, first of all, how would you build Amperity? And if you're going to build Vamperity, meaningfully in today's tech scene, you're going to do it at scale. So to do that, you're going to either come up with your own means of distributing the work to a bunch of cloud machines that you dynamically provision, or you're going to lean on a framework to do that. We chose to leverage Spark, which, if you've never worked with it, is a highly scalable analytics engine for large-scale data processing. And it leaning a tiny bit back, thinking about what Spark is improving upon, if you've ever used Hadoop or learned about Hadoop, is maybe 15-ish years old now, and is one of the things I think that at that time, 15 years ago, would be like where Google got a big, huge competitive edge, because it was able to solve a bunch of these massive data problems at a speed and scale that no one else had perceived to be possible at that point. But MapReduce, so Hadoop uses MapReduce, and MapReduce is not easy to use. As Clojure programmers, you actually all pretty are familiar with this, taking a problem that you're familiar with in the imperative context and then converting it into something that you can represent as a series of transformations and actions, or maps and reduces, right? And that's what Clojure does. It has at the very bottom a map and a reduce and a bunch of sugar around that. And then Hadoop basically takes that same concept of, like, we can take any imperative problem and convert it into this MapReduce framework, and then that lets our backend distribute the work to thousands or however many nodes are necessary to deal with the scale of the data you're dealing with. Now, that's really hard to use. I mean, 15 years ago was a huge deal. At this point, is getting harder and harder to use and deploy. And that's where kind of Spark slots in as saying, we'll provide a higher level abstraction for you to interact with the same kind of distribution of work, but make it a lot easier and make you not have to think about quite so many of the challenges that come up with when you have to shard your data, uniformly distribute it, deal with fault tolerance and things like that. And that's this little snippet, which admittedly is a contrived example of doing something like the TF-IDF index built construction, but offers a monstrous, this is like 100x performance improvement. And yeah, we're a Clojure shop. We love it and we live it. So, but when you take first shot at it, Spark and Clojure make a lot of sense together. You take the pure Clojure solution to just say pre-processing a row of data. So that's something that Yan mentioned is actually really critical to the quality of result that you get and how clean that data is as it comes in. You read the table data somehow, you spit it out into a vector of key value pairs, or a sequence of vectors of key value pairs. You grab the values off of all of those, and then you run those through pre-processing. And the same kind of thing here. Actually, this should be a map. I just realized. Sorry. The same thing. You kind of rewrap the same basic logic, and then all of a sudden you have the ability to distribute what was just a basic Clojure function, all written and tested in Clojure, pure functions, and then you get to distribute that across hundreds or thousands of nodes, or cores, I should say. Maybe nodes. I don't know. So to get to the point where you can have 1,000 nodes or however many executing your Clojure code, you need to figure out how to transmit that Clojure code onto your Spark cluster. So it's important to recognize that Spark does have features built in, and they're first-class features supporting Java and Scala. Spark itself is written in Scala. For distributing that code in an efficient way, in a way that kind of doesn't get in your face, and you don't have to worry about it quite so much. We're choosing to use this own kind of niche language, so we bring a couple of extra problems onto our plate by doing so. But most of them are pretty solvable and interesting in their own right. And Clojure does kind of put us in a good position to do this. By being pure, you have very little mutability to worry about when you're creating the kind of closure over the code to ship to the cluster. And there's the "it's just data" tagline that makes this a little bit easier. So immediately, an implemented IFN or I function would be quite serializable, as opposed to some other programming languages that might make it troubling. So in general, the Clojure core implementations of the Clojure Lang iFunction interface actually do implement Java I/O serializable. So we can just feed it to an output stream, and it will serialize the function. And I'll leave a link here in the slides, which should be available afterwards. It's actually really interesting how they accomplish that. It's a bit of Clojure magic or Java magic. I'm not sure which side, but it beyond the scope of this talk, but it is interesting how they accomplish that. But so every function is serializable. Why can't we just ship those iFunctions straight off to the Spark cluster and tell them to go? Well, the problem is that the Clojure runtime comes up on Spark and really anywhere, having no requires applied to it. And this means that if you were to have something that weren't in your core library, you were trying to invoke some custom function in a custom namespace, and you called it from within Spark without any thought about it, just by serializing the iFunction and shipping it over, you get this attempting to call unbound function. And we'll see this a couple of times as we walk through some adventures here. And that just means it has, that namespace is simply not available. We have no idea where that code is inside of your jar, or if there is a jar that has that code, or anything. It's just not there. So we have a third-party Clojure library called Amperity Sparkling, borrowed from, or forked, I should say, from Gorilla Labs Sparkling. Let's talk a little bit more about that. That takes care of the encoding of the recursively referenced namespaces inside of a given iFunction, so that when you call that on the Spark cluster, that it's actually required in all of the namespaces that you need to via the Clojure Lang RT, which is the Java to Clojure interop layer. So continuing on about serialization, like I said, we forked it from Gorilla Labs. We are deeply grateful for the amount of work they have put into it. Our additions have been very minor, bug fixes and things like that, but it's been tough to engage them. So we've kind of just went in our own direction. We'd love to see more engagement in there in the future. But so like I mentioned, we extended this, initially that Gorilla Labs sparkling, if you're thinking about starting this, will throw those attempted to call unbound function exceptions quite a bit, because its attempt to deal with that require problem is it says, oh, you're calling a function in this particular namespace. Great, I'll require that namespace and hope that your function never calls anything else, and which doesn't pan out, obviously. So we extended it to walk the I functions recursively so that you can find any references to any other namespaces and then just encode those onto the object stream and off onto Spark. And then when we deserialize it, we do the reverse, pull the namespaces, require them all via Clojure lang RT, and then actually we can call the function and it won't blow up, which is a big win. Booleans, again, this is kind of an implementation detail of sparkling, but it was interesting nonetheless. We found that the Java class Boolean, there's a bunch of different Booleans, especially if you're in Clojure land. The Java class Boolean, so the one you would make by calling Boolean false, for example, were always coming back as true every single time. After we closed over them, closed with an S, and then serialized them. So I'll step back 1 second and say the main way that you would transmit a value, a reasonably sized value, not like a value that's hundreds or thousands of megabytes, but a reasonably sized value into the scope of an executing Spark function is just by forming a closure with an S over it, and then Spark will kind of do a bunch of magic in the background as part of its serialization process to ship that value over. But for whatever reason, as implementation detail of Gorilla Labs and of our sparkling, those Booleans were coming across, and all we were looking for was basically the nil check. Is this a nil object or not? And it was not. It was always a true object, even though it was a Boolean false, right? So, and this is really confusing. You look at your logs, you look at all of your Aurora configuration, your Docker configuration, whatever it is. You trace the value of the environment variable all the way into your execution stack, and it's always false. But then there you go. Your little debug code is this little debug statement of code is still running for some reason. And then some Spark functions, like core built-in Spark functions, seem to actually sidestep the normal serialization path entirely. And that calls for, in our case, a gruesome hack. We're still a startup. We get to get away with those kinds of things for a little bit longer. So let's talk a little bit more about that. So consider the following Spark transform, designed to sort data in Spark by basically comparing a nested value that's inside some kind of, it's 3 layers nested map here. It's like map. That's a vector lookup. But it's pretty simple. It's like, find me the highest PK, basically, right? So you're looking at this, and especially if you had this appear in your code base a handful of times, you would immediately, as any good programmer would say, well, I should refactor this. I should not repeat myself. So you do that, and you get this cute little namespace, utils key, and you do the full decomposition. You've got key less than, which is what we've replaced this function with, and then key less than calls key pk, just again, so you don't repeat yourself, right? We feel good. We feel really good. This is why we became programmers. And we run it, but we get this all too familiar attempting to call unbound function. But this is a really interesting one. Look at this stack for half a second. We're calling from key less than qmark, this function, but we can't find the function in the exact same namespace as this function is being called from, key to pk. And this was a big WTF moment for us, because it did, and we went to the point of wiring up a bunch of debug statements into our sparkling library and running this through, and you could actually deterministically prove that it never ever called our library. So then if you dig into the implementation of sort by key, you find out that due to the convenience of Clojure to Java interop and the availability of a Java Spark API, because it makes sense for them, Scala is built on the JVM, and Java is obviously going to be the biggest mind share to get some participation from. So Clojure builds against the Java API for Spark, which is written and executes in Scala. Still all in the JVM, but there's a bunch of translation layers in there. This, if you're familiar with Java or you've done some digging in Clojure, actually satisfies the Java comparable interface. And if you look at how the Java version of sort by key is implemented, what it does is immediately pass it right through to the Scala implementation of sort by key, at which point the Java interface comparable is kind of magically converted into what is called a Scala trait, which is kind of Scala's version of interfaces, a Scala ordering. And we don't really understand, I mean, we haven't taken the time to learn Scala and understand why this happens, but it manages to capture the intent and seemingly the Clojure code of this function, but without actually requiring the namespace somehow. So that when you go to do this, you don't actually have that code loaded. Again, we're a startup. We took the easy way out. We just shipped this version. But it shows there's a bunch of depth there. Both in terms of trying to understand how Spark is working, and then on top of that, how Clojure is going, what kind of path Clojure is going to take in terms of its own code paths through that. Switching topics a little bit. So this is a Grafana graph. I'm sure many of you have looked at something similar to this. This is particularly a graph of the executor heap memory from the JVM as reported during the lifetime of one of these Spark jobs running the Vamperity matching algorithm. And you look at this and, gee, what's going on between here and here? It seems to be most of the job, really, right? Most of this very long job, even. And even so, look at this. This is weird. It's jagged, it's kind of short jags, and then huge cliff drop. Jagged, huge cliff drop. It's kind of hard to see the further you get down, but the pattern is clear if you zoom in. And so what section of the algorithm is that? That is the blocking phase. And I think Yen mentioned this in passing. Blocking, the crude attempt to blocking is you just have all of your rows, and you do the full cross product of every single one of those possible pairs of rows, and then you just run that through the rest of the algorithm. But that, the full cross product on 100 million rows gets really, really expensive really quickly, and doesn't actually provide much lift in terms of the quality of the result. So you apply some kind of heuristic to reduce the search space of the amount of blocking pairs that you emit. And so, but still, even with the heuristics, even with understanding that we definitely need to thin it down, this is the dominating vast majority of this job's runtime. And we have, so we have an assertion that is unproven at this point that high-level data structures, like for example, a persistent hash map, which is fantastic to program with, really makes it really easy to create immutable solutions to problems, has a bunch of performance characteristics that are really unappealing once you get to the point of allocating hundreds of millions of them in parallel on the same JVM. So in the future, we're looking at what happens if you swap out in the places where you can identify a bottleneck. And I think it's important to recognize that we have gotten 3 years into this company, having not had to walk away from the Clojure core data structures and say, no, that's nonsense, that's too slow. It's getting you a really long distance, but then when you get to these next tier of scale, you start to have to ask some pretty serious questions about whether we can incrementally find an extra 5% out of each one of these, and then in aggregate, that creates a huge win.
It's still 2.5 years, Chuck.
2.5 years? Yeah, sorry. Time dilation. So yeah, options there. There's a thing called the Eclipse Collections Framework. It used to be called the Goldman Sachs Collections Framework, which are a bunch of really well-tuned, high-performance, well-benchmarked Java data structures of all the types that you'd ever want. And they offer both immutable and mutable types based on what you're trying to do. So these sharp little jags followed by this big jag. What's going on here, right? So if you know a little bit about Java garbage collection, and we're using G1 GC here, if you know a little bit about Java garbage collection, these little guys must be the young generation collections. And they do seem to be collecting up a lot of stuff. So we genuinely do seem to be allocating a bunch of stuff that can be easily reclaimed. But eventually you run out of headroom on being able to do those. And those are, those young collections are really appealing because they, even though they stop the thread that they're executing on, they don't stop. It's not called a stop the world garbage collection where every single thread on the JVM has to be paused, potentially for like many seconds or even minutes in the worst case, so that you can do a full sweep. And it does do a good job of doing that full sweep, but it's highly parallel and things like that. G1, GC is especially good for that, but still very painful. You can see it is not a slow pause there. So we're going to see what we can do about that, and I'll come back to it. But having access to graphs like these that break down the behavior of your cluster from kind of a per executor level is incredibly critical, I think, to making meaningful progress on a bunch of the performance problems that will come up with doing high-scale data processing. Clojure or not, we do use Clojure. This is all collected and aggregated by Riemann, for example, if any of you have had a chance to use it, but would come up in any programming language. So let's pivot again. Let's talk about race conditions. So if you've worked with Spark or any kind of like distributed processing engine, you know that really what you're doing is you create a series of transformations and then you call a trigger action to start actually executing those. But in building up those series of transformations, you build up what is called a DAG, which is just the same math definition as a directed acyclic graph that determines, or rather describes, the execution order and dependence and lineage of all of the data that is flowing through a given Spark application. So doing it in this way allows us to split up work evenly. So if you put a careful thought into how your data is partitioned, you can make assertions about an equal amount of data as being given to each of your executors, or a roughly equal amount of data is given to each of your executors. And then if one of those executors should happen to die for some reason, then you only have to recompute that one partition, and then you only have to trace back, if we're dying trying to get the input from stage 0 as stage 1 completes, all we have to do is recompute the pieces of stage 0 that went missing. We don't have to start from scratch and recompute every last thing. And that's honestly a big piece of one of the big pieces of where that 100x speed up from Spark to Hadoop would come from. But understanding when, where, why your transformations are actually being executed is pretty tricky. You could think of it maybe as pretty easy here. There's only 7 boxes up here, but this program is not doing much more than doing like a set difference on two sets. It's a very, very simple program. In practice, a production Spark application like the ones that Vamperity might use could be hundreds or thousands of stages, and you need a big monitor or a lot of scrolling to read through it. So let's look at how a race condition can emerge in a world where you're doing programming against a DAG. So let's think. We're kind of leaning back on the specifics of Yan-Yan's talk here. So we form these transitive closures. So those are the complete components. And those are kind of like the pre-clusters. You could take those as clusters and they would be pretty meaningful, but there's a lot of refinement you can do in here that is valuable, but is expensive. It's expensive to do that refinement, regardless of what algorithm you're choosing. So we, kind of early on, we realized, okay, there's clusters that are have hundreds of members or thousands of members, and then you go and dig into them, and they're it's all nil fields for the entire record, except it has the same foreign key all the time, and it's like what the storefront uses to ring in a sale or something like that. So it's useless data from the perspective of a customer-facing firm that wants to have better engagement with that customer, because that's not a real customer, it's just some sort of test data or something like that. So we would set aside the huge clusters, write them to storage, and then read them back to storage, and then union them back with the regular clusters after we push the regular clusters through what we call a more expensive clustering process. Now, in practice, when we did this, we observed about 2 or 3% of these huge clusters that we're trying to read back from storage would go missing. Everything else would be correct and look great, and the rest of the supersized clusters, as useless as they might be, were still correct in there. But there's kind of a random selection and non-deterministic between run to run on the same input data. You'd get a different set going missing. So at that point, you have to start asking who is triggering this code, when, and why. So to understand that, again, I mentioned Spark has kind of two classes of things, of kind of programming actions. It's a terrible word to use, but there's transformations, which are like maps, filters, things like that. And then there's actions, which are like reduces, counts, group bys, things that force a bunch of actual shuffle action to happen. So if we look at where our first action is in this DAG, it's all the way down here, which on its face doesn't necessarily seem wrong. But that means that when you actually go to execute this, basically what happens is this is all kind of flattened into a series of, comped together as a series of function calls. And that means that this function call and this function call are happening simultaneously. So that means that it becomes entirely possible, if your data set's large enough, for you to reach the EOF on this read before you've actually finished, genuinely finished writing all of the data. Because it's happening on a bunch of different machines on a bunch of different threads. You need some coordination to get that flag to say you've actually fully finished. Okay, that seems like a pretty clear race condition. And if you to confirm that theory, you say, okay, what would you do? You'd move the action up to here to force the writes to finish all the way before any of the reads started. And yeah, that did solve the problem. But this is still like awkward and kludgy. Like the fact that we did this loop around where we write to storage and read right back from storage is representative of a bunch of architectural cruft. So you can enhance that one step further and just filter that out essentially in memory, and then you can keep the action down at stable ID, and then due to kind of guarantees about how Spark will treat its in-memory constructs of a data set, will guarantee that you won't stop reading from here until you've finished everything that can be consumed as part of its input. Okay. So let's talk a little bit about using Clojure in a high-scale environment. On its face, Clojure and its standard lib are like really fantastically friendly to high-scale data applications. Lazy sequences are essentially exactly what you'd want when you're thinking of building, or you're thinking of dealing with sequences that are potentially huge, and you want to deal with them in a streaming fashion without blowing out the memory of the machine that you're dealing with, or the machine that you're executing on. And then that's a good bridge into places. For example, there's a ton that we've leveraged, but for example, the partition suite, partition all, partition by, that provide a tremendous amount of value. Again, it's still lazy, so it's even better. But I'll make a caveat and say, once your data set gets big enough, it becomes harder and harder to convincingly say that everything about the output of a transformation you've applied to that data set is 100% correct. It's really easy to eyeball or automate a system that operates over 100 rows to identify when 1% of your data goes missing. When you've got hundreds of millions of rows and 20 million of them change every single day by design, it becomes much trickier to identify concretely when 1% of your data set goes missing. And that's what we actually had happen to us, or that's what Amperity had happened to them. We had an issue where about 1% of our input data set was going missing. And it's an awkward, embarrassing, cute little bug. So on the left-hand side was the buggy version of this, where this function is basically supposed to look over the key space of an input data set and then create split points upon which, if you built ranges around those split points between each of those two split points, it would be roughly uniform. You'd have roughly the same number of rows in each one of those, or the same number of bytes. And the core bits of it worked, except when we dug all the way into it, we found that last range, the range that goes from that last split point, which is not the max key, it's the last split point to positive infinity, was not being included for some reason. And it was painful. Like, it took weeks and weeks of iterating on this job that takes 3 or 4 hours to run and a bunch of preconditions to get set up just right. and you run the test and you have some hypothesis proven or disproven, and then you don't, your only other option at that point is again go kick off another 3-hour test. So yeah, it took a while of grinding through it, but and then you work your way back up from the first place you see the problem, or rather the last place you see the problem, where you observe it in the output, all the way back up to the place where you can find the root cause. In this case, it was all the way, this is like the first thing we do. So it took a little bit of time to say like, nope, that code's fine, that code's fine, that code's fine, until we get to something so shockingly bizarre, or not bizarre, but shocking, I guess, that we could be dropping 1% of our data on the floor every single time and not really noticing it. This is conflated in some other issues that made it harder to notice in practice because of how things would be cached and some differences when you're running from a blank state versus you have had a job run before you, but weeks and weeks to a 4-character change. And this is not Clojure's fault. This could happen in any programming language. So wrapping up here, some quick Spark and Clojure takeaways. It's like I said, I think it's probably as good as any non-Scala programming language. If you knew Scala and we're going to start on a big Spark project, I think that seems like a really good choice. But other than that, Java or Clojure seem like great choices. And if you choose Clojure, then you get to program in Clojure, which is always fun. I showed that graph before, and I'll say again, invest in your metrics early, heavily, and often. We've done a number of big revisions on how we approach metrics and graphs against those running Spark jobs. And I'll say the biggest breakthrough is being able to see per executor breakdowns of the CPU, memory, garbage collection, and network and disk I/O, overlaid with essentially stages that can show you this is when this part of the application is happening, this is when this part of the application is happening. Otherwise, you're kind of stuck matching timestamps, and it's very ad hoc, and you can't really eyeball things too well about, oh, that seems horribly slow today. I'll say, Spark is fantastic. I'm not aware of a tool set that is as mature as it, that does a similarly quality job, that has as much community mindshare. But that said, don't expect to be able to get to high-scale Spark efficiently without spending lots of money on experiments, learning about JVM internals, learning about how Java garbage collection works, and how to actually tune it to do specific things based on what you know about your workload. Learning how to trawl the official Spark Jira to figure out if someone else has run into whatever insane exception you're seeing, or whether you're doing something gravely wrong. Or learning how to build your own Spark binaries, and in turn how the Scala compiler works, and in turn how the Scala versioning system works, But this seems like a horror story, but I'm going to tell you, this is the best moment Amperity has ever had. We are more poised to do something really fun and really special than we have been along this whole ride. We've just finished scaling. We're at 22 concurrent customers in our production environment right now. In the last 12 months, we've almost doubled in size from 36 to 65. For our biggest customers, we match over 100 million records every single day inside of a daily SLA window that we hit pretty much every single day. And it's worth noting, it's shocking to me. I don't get to interface with customers a ton, but it's shocking to me to learn that customers are blown away that it's even possible to do this. Previously, in their old life, before Vamperity, they would contract a vendor. The results would be much lower quality, and it would be so expensive you could only really justify doing it quarterly or annually or something like that. And you'd only be paying it for just that once instead of a constant everyday influx of fresh data. And we're hiring, if you didn't know. We continue to grow. Talk to me, talk to Dave, and let me know if you're interested. I don't know why Yan Yan wanted to put this slide on here, but she wanted to. It is open for interpretation. Yes.
So the other night, for the first time, I was trying to figure out how I would access a Scala library from Clojure.
Oh boy.
And it led me to one or two libraries out there that purported to make the process a little bit easier, because apparently Scala classes compile down to some things that some different Java classes that maybe isn't quite the way they're namespaced in Scala, and so something to make that process easier. Is there a library you use? Is there any other tricks to know to interact with a Scala library?
The tricks are isolated into that Amperity sparkling library at this point. And really, it's a pretty small number in this case because, like I said, we get the benefit of getting to go through the Java Spark API, which has natural interop inside of Clojure.
So everything that's written in Scala, you're really interfacing with the Java.
Yeah, but that opens, like I mentioned previously, that opens us up to a bunch of bizarre edge cases where you go through this conversion path that no longer are you calling your custom serialization code that has whatever magic you need to survive. But yeah, I think was it From Scala is the main one there, and I've used it. It's solid. I've toyed with it, and it might be the solution to some of those sort by key problems. But in general, it looks really scary. $$ dot apply.
Okay.
Yes.
I was wondering if you can go back a few slides to the diagram where you were talking about filtering out, right here, the filtering out the huge clusters and filtering out the regular clusters. Is that so the difference between this slide and the next slide, I was wondering what's going on here. Is the filtering out, is that just a series of predefined filters, or is that another clustering algorithm?
It is just it's a Spark filter, which is basically the same as a Clojure filter. But it happens distributedly, and the fact that it's happening as kind of a first-class Spark function guarantees that it will consume and output all of the data before it emits, or before it dies, essentially, and allows the downstream stages to proceed executing.
Then what was the difference between that and the previous?
So in this case, there's a real race condition in that this read can complete, or think that it's complete, I should say, before this write is truly complete. So there could be lagging partitions, like say a really huge skewed partition that is taking a long time to finish. And then you get to the end of what your database or your file system says, this is the last file in the directory, or this is the last byte in the file. And then you're like, okay, great, I've read all my huge clusters, I can union them back in. So there's a race condition between finishing this write and reading a full set of clusters.
I understand. So, but so I'm reading this right. The second slide where you're saying you're filtering out the huge clusters.
Yes.
And then the next slide says filtering out the normal clusters. Is that the regular clusters? Is that just the same thing, or?
They are the complement of one another.
Right. So okay. All right.
Yeah.
So in the previous slide, what I saw is that for some reason a classic barrier wasn't being applied at the end of that step. I was a little bit confused about the semantics going on here.
Yeah, the real trick was that we had kind of screwed up and we were trying to collapse a couple too many transformations into one map partition call. So what we had done initially was try and, it's really what it says, filter the huge clusters and write them in one map partition. And map partition has the property, it is a transformation, not an action. If instead we had used for each partition, that is an action and would have forced a full realization of whatever transformations we had built up until that point. Yes, Spark.
I'm not sure if this question is for you or Ian yet, but
Get up here.
my question is, for the union find data structure, do you use an imperative version of that data structure or a functional version? And the reason I ask is because union find is usually an imperative data structure, and I personally have like a little functional version I've developed for myself. And I've thought about open sourcing it, but I don't know if anybody else in the world would care about it.
Yeah.
So
I mean, we hit a place with union find where essentially we needed that. There are some options. They're fairly new actually for a distributed union find with a globally optimal solution, but it is pretty new, hard to implement, and we weren't aware of it at the time we were first building the system. So the only option at that point is to do a single-threaded union find, or a single host union find at best. So our basic process is do all the scoring, all the blocking, all the scoring, and then spit that out back onto the driver, which is kind of the main program, the coordinator of a Spark program. And then we would run a highly optimized integer-based union find that is mutable to do the actual collection of those transitive closures. And then we'd reparallelize those transitive closures back into Spark for the rest of the pipeline. But I would love to see that. That sounds really interesting. Yes.
I'm just curious. When he was talking about serializing function, was there even an option to actually upload a bytecode? I mean, jar or...
So you do upload a jar, and that is where the code is actually living. But so I think it's important to recognize, and I kind of glossed over this, I believe, I haven't tried it, but I believe if you were to defen and name every single one of your functions and then only refer to them by name, some of these, large number of these serialization problems would go away. But we all program in Clojure, we all love writing lambdas. They are hyper efficient and elegant in their own way. So this problem really comes up when you're dealing with lambdas, most specifically. In that case, that lambda gets serialized correctly, but all of the reference namespaces inside of it, you don't know whether they're going to be there or not.
I guess my question was more if you can actually transform your code into jar and upload a jar instead of
I see what
any
you're saying.
serialization.
I have not. I mean, that seems quite viable, but it is, for the most part, expected that your jar be included on the initial class path when you start the executor. I haven't seen a pattern around hot loading a jar.
Yeah, or create a flat jar.
Yeah. Yes.
So actually, I did some stuff like that with a actor framework for .NET, and it's really, really easy if you have a compiled static environment where you can then produce an assembly or essentially a jar file, but it also will tell you all the dependencies, so you can upload all of them trivially.
Yep.
Seems like
yeah, it seems quite tractable. Yeah.
Yeah. Seems like you could use a solution like that.
There's also another solution that is kind of in the direction that you two were talking about. I think it's C. Grand's work called Ouroboros. And he presented it at the last Conj, I think, about 12 months ago, a little more than that. We explored it. It was pretty. It had a bunch of issues that we couldn't get around easily. But I think that direction is very viable, and as we grow a little bit more and get a little bit more time to invest in better tooling, more efficient tooling, that's definitely the kind of direction we look in. That problem especially comes up when you think about doing a live REPL session into a running distributed Spark cluster, and you'd like to be able to write new functions or lambdas on the fly and have them ship over. That's kind of the core of what Ouroboros solved, with caveats. Yes?
You guys thought about real-time application?
Absolutely, yeah. I mean, and I think Yan, maybe she did. That was one of the first things we took a serious whack at. Is you would look at a visitor's website data, an anonymous visitor's website data, but you could tie together with a bunch of fingerprint style information. You can something like 50-ish bits of identifiable information are available to each website that you visit, even if you aren't logged in. But most of the customers wanted to be able to do that, say, have us ingest some data in a streaming fashion, turn it around in less than a couple of seconds, and emit that back so that they can load it in an asynchronous JavaScript widget. And through a lot of different reasons, we found it ourselves a ways off from that kind of performance. But we also, at the same time, were finding that there were tons and tons of customers that didn't even need the real-time version. They were blown away by the fact that you could do it more than once a quarter. So we doubled down on that side of it. And I think as we grow, we might loop back and look at that. I mean, obviously, as the internet continues to grow, as the industry continues to grow, that will become more and more possible or more and more viable, or necessary. But right now, we've found a sweet spot in just doing these kind of daily batch processing.
Just to add to that a little bit, we actually invested in a lot of work on real-time pipeline early on. What we found is that out in the real world with large companies, they don't actually have many real-time capable sources of data. And so in most cases, they could at best get us, especially voluminous data, on a sort of file-oriented, once daily basis. The other thing, which is a little more subtle, is the value of what we do is in the composition of all this data. And that's only valuable against data that accumulates over a long period of time, right? Like what you did in the first 10 minutes of your Amazon session ever is like maybe sort of interesting, but what you've done over the past 10 years is like really, really interesting. And so that applies pretty generally. So these days we've spent a lot of time looking at real time in a little bit more nuanced way, where it's less about, hey, can we do this thing that can take your last 20 years of data and put it all together in sort of in a completely quality optimized way, versus how do we incorporate what happened in the last few minutes on top of that, and they're actually different problems. So lots more to come there, but it's not just take this thing and like make it faster. That's actually not very valuable.
Yeah, it
in
would
the
be a
real world.
parallel stack, I would think, to do to real time. Anybody else? Yeah.
Sure. So you're dealing with some fairly large data sets.
Yes.
How are you managing testing and reliable QC with a reasonably representative data set?
Yan, you want to take that? And how do we verify that our stitch results are right when we don't have a labeled actual correct result to compare against?
Oh, that's a
Right?
good question.
Right?
Yeah.
Is that the question?
Yes.
Yeah.
Is it a question? Okay. So first is obvious comes from how you label data. Whether you use the label data for training or use the label data for result validation, right? And what we do is we actually have a pretty unique technique. We don't look at the data. We don't randomly sample the data. We sample the feature. So if you have like John Smith with the same zip code and like Mary Johnson with the same zip code, in our eyes, they are the same data. It's like when I have like mechanical engineering, electrical engineering background. So it's like when you look at a signal, you can look at a signal in the time series or frequency series. So like a sine wave will be continuous wave, but have only one frequency. So we actually sample on the feature space. So we reduced the sample point to a very like we're talking about hundreds of millions of data. We can reduce like 10,000 pairs. That's truly unique. That's not like everything, but it has a good representation of the data's characteristics and then the landscape. Then we label those. And we also do a lot of some like rule-based auto labeling. So say, hey, if you have the same name, same email, you are the same person. And we only use the manual labeling to label the ambiguity case. Yeah.
We also have some traps in the data pipeline for sort of the less nuanced specifics of the data. So it was alluded to earlier, but for example, if there's a big shift in that cluster error metric, we'll sort of stop the presses, alerts go off, and we'll say, hey, let's go take a look. Did the data really change? Did we get a bad data dump, or was there something algorithmically wrong? So it's a combination of many layers of things, and obviously there's always going to be a few specific data rules that you program that are specific to a customer, that aren't sort of general stitching metrics, and those are just things that you have to do to be able to do this reliably over time when the data's changing and you want humans to be out of the loop.
Sorry, can you just clarify a little bit on that? So it sounds like you're using unsupervised learning algorithms.
Well, we are using supervised learning algorithms.
So you're labeling data using features that you created using.
Yes, so we have the feature engineering done first, and we created the feature vector for every record pair. And so we have like pairs, and we label them only for the ambiguous case.
I see, and that's what you were talking
Yeah,
about.
we don't use unsupervised learning because like, a lot of them are partition based. So you have to say how many number of clusters you expect. Like there is no way we know. And we do prototype some semi-supervised learning, like active learning. So to carefully solicit user feedback. You don't need to label a lot of them, but they kind of like converge. Like by asking each question, they're detecting your decision boundary. So they converge way faster. So there are a few things, yeah. It's just a question.
So after feature engineering, what kind of order of magnitude, how many features do you usually wind up with?
It depends on the semantic fields we have. So the more semantics you have, more features you have. So for like a name, for instance, we could have range like 8 to 10. I guess like depends on name's popularity and how like are you the same name? Like are you female change the last name, or you just have like a name typos? Yeah, to capture those.
Anything else? Thanks everybody for coming. Thank you so much.